Hello, good morning, and welcome to the AEE Canada East webinar focusing on heat recovery technologies. It's the first one of the year, so we hope you enjoy it. Before we get rolling, we always like to give a shout out to the chapter sponsors. Of course, the sponsors of our chapter are key and critical to keeping programming like this flowing, and this is our first opportunity to thank the sponsors for 2022. So if you see your company's logo up there, you can give yourselves collectively a pat on your back. If you don't and you think it should be there, make sure you reach out to us. Like I said, the sponsors are really key and critical to making sure that chapters like ours can function. Of course, we are a chapter of the Association of Energy Engineers. It's a large international association, over 18,000 members worldwide. There's chapters in over 100 countries. I was chatting with our presenters earlier this morning, and interestingly, a year or so ago, the international chapter count dwarfed the domestic chapter count in the United States, which was a pretty exciting thing for us to see. The Association of Energy Engineers is a robust international group, and I've always found it to be a useful group to be part of for me professionally, and I trust that those of you who are on this webinar might find the same value. You probably have noticed, we are in webinar mode, which means that from our perspective, it's quite sterile, and the interaction that you have with us is through the Q&A panel. So if you notice at the bottom of your screen, if you have a question during the presentation and you'd like to ask it, you just enter it in the Q&A panel, and Mark and I will moderate those questions with the presenters and then try to make sure everything gets answered. But certainly don't hesitate to ask questions at any time, but understand that we may only answer them towards the end if that's what the moderators feel is appropriate for the presentation. And of course, you're attending this webinar, and the Association of Energy Engineers Canada East chapter is really pleased to be able to offer you professional development credits for attending these things. So the key there is, though, that we're only really able to do that for members of the chapter. So if you're attending this webinar and you wish to get a PDH hour credit, you'll need to join the chapter, and we encourage you to do that. You can go to our website and follow the links to join. It's a pretty modest $50 a year to be a member of the chapter, and of course, throughout the year we hold webinars and other activities, and you can gather these professional development hours along the way. So if this is of interest to you, please make sure you go and do that. So without further ado, I'll ask Mark to introduce the speakers for today.
Great, thanks, Andrew. So today we have Robert Tribe and Antoine Hoffer from Thermal Energy International. They're going to be talking about condensing, heating, and heat recovery technologies. I've got an intro here for Robert. I'll try and go through it quickly. Robert earned his bachelor's in chemical engineering from the University of Waterloo and his master's in environmental engineering from the University of Ottawa. Mr. Tribe has over 30 years of experience in carbon reduction and energy efficiency and environmental fields. Mr. Tribe has completed conception, development, design, and implementation of energy recovery and environmental improvement projects ranging in value from $100,000 to roughly $10 million, along with numerous energy conservation screening studies and detailed feasibility studies resulting in energy projects of various types. So that includes industrial, institutional, commercial buildings, and various sizes of facilities during his work with Jakes Woodford Environmental, which is now Stantec, and Thermal Energy International. Mr. Tribe is recognized as an expert in carbon reduction and environmental technologies by the Sustainable Development Technology Corporation of Canada, for whom he reviews and evaluates technologies to assist in allocation of Canadian government funding. I did not know that. As a Chief Technology Officer, he has scrutinized and recommended offerings and technologies for acquisition and incorporation into mainstream product offerings, and he has led and supported efforts to raise capital and support for these key corporate initiatives. As a COO, engineering and sales manager, he has integrated and grown sales of these new offerings for Thermal Energy and Stantec. And we have a co-presenter, Antoine Hoffer. He graduated from Montreal's Concordia in 2004. That's where I did my master's, so shout out there. Worked exclusively as an energy efficiency engineer for the past 18 years, specializing in pulp and paper drying, efficiency and heat recovery for 9 years as an employee of the company Enerquin Air, and for the last 9 years as an employee of Thermal Energy International. He's worked on energy and carbon emission reduction projects in institutional industrial sectors, while specializing in condensing heat recovery technologies and steam and condensate systems. So welcome to Robert and Antoine, and I will hand the floor over to you.
All right. Thank you very much, Mark, for that kind introduction, which I wrote. And I'm very honored that this is going to count as a professional development hour. I'm feeling quite useful in that regard. And so let me just make sure that we've got the screen going. Boom, boom, boom. Okay, Antoine, we have a screen up? Yes, okay, and here we go. So thank you for joining us. Thanks, Mark and Andrew, for asking me to present. I've been working with condensing technology since I left school, and even today still, although the technologies have become more mainstream, I see them misapplied very frequently in the field. And so I thought it might be useful to talk a little bit about condensing technologies and how critical integration is in successfully applying condensing boilers or condensing economizer technologies. So I'll do a quick overview, definitions just to provide some context, and then I'll talk about the technologies themselves. Then I'll talk about some considerations for technology selection. So the overview, you guys all know this: boiler plant 75 to 85% efficient, 15 to 20% goes up the stack. Worldwide, fossil fuels, if we look at the old days of power generation at 35% efficiency and boilers at 80% efficiency, during the fossil fuel crisis, fossil fuels were used at an average of 50% efficiency, which is pretty crazy. Steam is the most common heat distribution medium, but it's falling out of favor because of inefficiencies we'll discuss as a part of this presentation. Condensing technologies offer an excellent efficiency improvement and boiler replacement option. They're newer high efficiency technologies, but there's some fear of change and dependability. Status quo is comfortable, but inefficient. In order to take advantage of condensing technologies, you often have to convert to hot water systems, and conversion to hot water systems are expensive and expansive, particularly in old infrastructure buildings, and therefore provide extremely challenging returns on investment. So that's an overview of the issue. A few definitions, just so we have context. Typically, when I'm talking about efficiency, I'm going to be talking about combustion or thermal efficiency, which is strictly the efficiency with regards to how much energy we're losing up the stack. It's the heat that the combustion produces and is delivered to the system minus the heat that goes up the stack. It doesn't account for radiation and convection losses. People will often, and I'm not defining these terms. Different people use different names for these terms all over the industry, but I'm just defining how I'm using them. Boiler or fuel to steam efficiency. That's the boiler useful energy divided by the energy input. It's obviously lower than the combustion or thermal efficiency because we do have radiation losses. Some places will even include the deaerator steam load as a steam loss in this boiler to steam efficiency, because the deaerator can have a significant steam load. Do you consider that useful steam or not? That determines how you define your boiler steam efficiency. So every plant even defines that number differently. And then there's a greater concept of a system efficiency, which is like how much energy actually gets to the end user, how much energy reaches that bedroom in the hospital or reaches that process heat exchanger in the field. That's more like a system efficiency concept. So typically in this presentation, when I'm talking about efficiency, I mean combustion efficiency. Combustion efficiency is typically 75 to 85%. Boiler or fuel to steam efficiency, typically 70 to 80. The delivered efficiency is typically 55 to 70, quite low. And that's a result of this. Here's a Sankey diagram for a typical boiler showing 100% fuel input. This would be for a natural gas boiler where we have 18% losses in the stack. So that would be an 82% thermal efficiency. But as we know, we lose energy in steam traps, condensate, pipe work, insulation, blowdown, standing losses, pipe leakage. So typically, most people who use steam systems would agree the amount of heat that reaches the end user is between 55, this might be on the low end, but between 55 to 70% of the heat actually gets delivered to the end user, and the rest is lost and wasted in the system. So quickly, I'll define sensible and latent heat. So sensible heat is energy from a temperature change. Latent heat is energy from a phase change. Interestingly, these define as well the difference between higher and lower heating value. Lower heating value is basically the heating value of the fuel excluding the latent heat. And the reason the concept of lower heating value was invented was because latent heat was considered unattainable and useless. It was even considered a menace in that if you got cold enough in your exhaust gas to get the latent heat, that meant you were condensing. If you were condensing, you were ruining your boiler or you were ruining your stack. And because of the condensation and corrosion. And so in fact, you wanted to avoid using that latent heat because you didn't have systems that were designed and capable of taking advantage of it. And when we go to China, we often still see people saying they're 98% efficient. And when we tell them that we can do heat recovery based on a lower heating value, we actually tell them that we're going to bring them to 112% efficiency. And that's very hard to convince people, but based on lower heating value, that's the case. But the truth is, of course, sensible heat is quite useful, and that's the whole purpose behind the condensing technologies. Very quickly, I just show this slide to make the point. Sensible heat's a big, or latent heat is a big thing. The sensible heat required to bring water from 0 to 100 Celsius. I'll apologize now. I'm going to be going back and forth between Celsius and Fahrenheit. But the energy to bring water from 0 degrees to 100 degrees is about a sixth of the energy required to bring water at 100 and turn it into steam at 100. So the energy required with no temperature change, just a phase change, is 6 times greater than the energy required to bring that water from 0 to 100. So that's the latent heat, and I'm just making the point that it's big. It's a lot bigger than a sensible change, a small sensible change. So over no temperature change, you get a tremendous amount of heat. So a few definitions. Now I'm going to talk technologies a little bit, and I'm going to talk just about a few slides on condensing boilers and condensing heat recovery technologies and the basic types. So without condensing of vapors, why are we doing this? As I've mentioned, without condensing of vapors in the flue gas, we're limited to roughly 80% efficiency in a gas boiler because a gas boiler has more water in the exhaust, and about 85% efficiency in an oil boiler. But condensing boilers or condensing heat recovery units can bring system efficiencies to 99% plus. And I'm going to give an example later that you can even be over 100% on higher heating value. But how? How can we do that? Well, simply, we're going to cool the exhaust gas. So boilers have an exhaust gas, and we want to cool it more than steam boilers have done in the past. So we use indirect tubes. We either put tubes in the exhaust gas, just like a traditional feed water economizer. The cold medium goes through the tube. We call that indirect heat transfer. Or we can use direct contact. We can take that flue gas and shower direct contact water onto that flue gas to cool that flue gas down. By cooling the flue gas, we condense the water vapor from the exhaust. Of course, when we burn fuel, we're basically making steam on the wrong side of the tubes, because when you burn fuel, you're burning C's and H's. When you burn C's and H's, you make CO2 and H2O. And if you're making H2O as a combustion product, it means you've got steam in your flue gas. If we can condense the steam out of that flue gas, we make a big energy efficiency impact. But now we've got to be corrosion resistant, and we've got to be connected to a suitably cold load. So that applies to all of the condensing technologies, condensing boilers, condensing economizers. They all bring you down into that condensing space, but only if your load is suitably cold. This is a key aspect of the integration. and they must be corrosion resistant, which is why, again, the old lower heating value and being fearful of condensing in a flue gas or boiler system. So why is it a big deal? First of all, I have to apologize for this. The term efficiency really gets me. An efficient heat exchanger, right? If I make a heat exchanger infinitely large, I can take the most inefficient heat exchanger and do the same job as the most efficient heat exchanger. So when I'm talking about heat exchanger performance, I'm talking about practically achievable with normal equipment sizes. Of course, the worst heat exchanger in this graph could achieve what the most efficient heat exchanger achieves if we make it absurdly large. So these are practically achievable efficiencies with different technologies. And as we know, I'm in Fahrenheit now, so the y-axis is your efficiency, thermal efficiency, boiler efficiency, which means if your exhaust gas is the same temperature as your combustion air, I got combustion air coming in at 60 F. If my flue gas is 60 F, I'm 100% efficient thermally because I put in 100 units of fuel into that combustion air, I heated it up, and I cooled it down to the temperature it started at. That's 100% thermal efficiency. So this is a graph simply showing that conventional boiler feed water economizers, which would be made of carbon steel and frequently fail, they typically can cool your flue gas down maybe another 100 degrees F or 200 degrees F, and your overall efficiency goes up 2 to 4% with a traditional feed water economizer. But the interesting thing is it's not a linear relationship. So as we're cooling down the flue gas, it's linear until we hit the dew point. The moment that we hit the dew point, we begin to condense and the reaction is exponential. And so the more we can cool the flue gas down, the better, but it's not a linear relationship. It's most important to get the high efficiency that we're linking into cold users. Otherwise, we can't cool the flue gas down. So again, this is a graph of exhaust temperature versus thermal efficiency and the types of performances you can get from these different technologies. So a little bit more on that, because the bottom statement on this slide is one of my favorite statements. It might be one you're aware of, but it's not one that's commonly known. So I've explained the dew point and the vapor, but the bottom statement's the one I love the most. There's more heat available between 140 and 100 F. So over 40 degrees, there's more heat available than in the previous 350 degrees. So if I cool your flue gas from 400 to 140, I get less energy than if I cool it from 140 to 100. And so that's why these low temperature sinks and integration becomes so critical. That integration determines what part of this curve your system's going to perform on. So now I'll talk about the technologies. We'll start with
Robert, it's Mark here. I don't know if anyone else fully captured that, but I'm just on that previous slide. Can you go over that just for me one more time? Because
okay, I'll show it to you on this slide because I think it explains it better. As I cool, this only goes to 300. As I cool the flue gas, and I'm glad you asked because Mark, if it's not clear to you, it's not clear to everyone. As I cool this flue gas from 300, so this doesn't show 400. My statement here was from 400, which is also true. But as I cool from 300 to 140, my total efficiency improvement, I go from 83 to 86%. So I cool from 300 to 140, I get 3% improvement. But when I cool from 140 to 100, I go from 86% to 95%. I get a 9% improvement over those 40 degrees, but I only get a 3% improvement over the previous 200 degrees.
I see, okay.
All right. So now I'm just going to look at the technologies quickly before we discuss integration. So again, I use the two terms that are key are direct and indirect, which means that the hot and cold sides either are in direct contact or they're heating through a tube or a wall. We're talking about boilers and economizers. So here we go, 4 categories. First, condensing indirect contact. I don't even like calling them boilers. They don't boil a damn thing. So it really frustrates me that the whole hydronic world still calls them boilers, but they do, so I'll still call them boilers. Basically it's quite simple. I like this schematic on the right, although it's kind of a hacked schematic. The basic thing is that it's showing is you've got combustion air, you've got a flame, but the flame is on the outside of the tubes. Your water's coming in, cold water coming in the tubes, getting heated by the flames, just like in a boiler, except we're not boiling. And the cold water comes in and goes out hot. The condensation happens on the outside of the tube. So on the outside of the tube, this water, that's not your heating water, that's not circulating water, that's the water you're condensing from the flue gas. So that water becomes a separate stream that you can sometimes return to process or sometimes you put to drain. But your condensation happens on the outside of the tube. The heat is transferred to the inside of the tube, but your heating medium is separated from your flue gas. So that's an indirect contact condensing boiler. Cold water in, hot water out. The cold water in is so cold that your flue gas is being cooled to below that dew point and you're condensing water out of the flue gas. That's common to all of these technologies. Another way to heat water, which is very interesting, is a direct contact condensing boiler. So it's the same thing. I'm heating cold water and I'm making hot water and I'm cooling the flue gas to below its dew point. But the difference is I'm doing it with direct contact. So here I've got a burner and the burner is literally in a shroud underneath a shower of water. And so the flue gas comes out of that shroud, is in direct contact with a shower. It's like spraying a hose on top of above a burner. And so the water that's heated is in direct contact and you get a hot water outlet. These devices are very cost effective because there's no pressure vessel here. But I'll talk more about the pros and cons later. So technically speaking, I can call it a few things. It's a wet scrubber with a burner in it. Or it's a burner with a shower being sprayed over it. But in the end, you can get extremely good approach temperatures. Again, I'll talk about that more in the benefits. So this is a hot water heater where the flue gas touches the water. This is a hot water heater where the flue gas does not touch the water. Both of them are used to cool the flue gas to below its dew point so we can get the latent heat. And now we're just looking at the same things without a burner. So the economizers, a condensing heat recovery indirect contact economizer is just the tubes from that indirect boiler, but you don't have a flame, you're just using waste heat. So it's just fin tubes really. Typically you could put in cold water at 40, you could cool the flue gas to 60 degrees or less. And the most common is that these are stainless steel with aluminum tubes. They're manufactured by a number of people, but it's the same concept. Cool the gas to below its dew point to recover that latent heat, and you have to build accordingly, all stainless steel, no more carbon steel economizers if this is the goal. And now we have the direct contact condensing economizer, which is this without a burner. And we don't need a burner because we're using waste heat. So you take your boiler exhaust, you take your waste heat, you put it in here. It's a wet scrubber. Water flows through and heats up. And that's a direct contact economizer. Here you can kind of see there's sometimes packing. Most frequently, some kind of packing can be random, can be structured, can even be an open tower. But this is a direct contact condensing economizer. So you can see these 4 technologies are really just 2 technologies, and all they are is heat exchangers. And the only question is, do I have a burner in it or not? So, the 4 technologies really reduce quite simply to direct or indirect contact heat exchangers with or without a burner. All right. And then I like to show this slide as well, because when you're doing this heat recovery, this is almost application, which is the next subject, but I wasn't sure where to slide this one in. Something else to consider is very often the feed water economizer it's always one boiler, one feed water economizer, and the feed water economizer addresses only the heat sinks related to that specific boiler. However, you can very often recover heat from multiple sources and deliver to multiple sinks. You can really look at a economizer as a free hot water boiler. And that economizer provides you with free hot water. You could use multiple boilers, you could use multiple different process sources, and then you can deliver heat to your utilities. You can heat boiler makeup water, you can deliver heat to air heating, you can deliver heat to perimeter radiation, to reheats. So, the thinking and the integration of these technologies should go well beyond, I'm going to recover from the boiler to deliver to the boiler, even go beyond, I'm going to keep my heat recovery project in the boiler plant, or I'm going to keep, my heat recovery from a dryer and just heat that dryer. You should look more broadly in the facility and see what you could do with a free hot water circuit that, a few hundred feet of piping is not often a project killer, especially in today's world of sustainability and carbon reduction.
Can I ask another question, Robert?
Yes, sir.
Somebody had the same question I did. So for the direct type, does anything happen to the water as it comes into contact with the flue gas? Does it become like acidic and all that? And is that a problem if you're feeding that back into the boiler? How do you deal with that?
It's a very good question, and it sounds like one of the considerations for technology selection. And I think I'm just about to get there, so I'm going to cover that in 1 or 2 slides. All right, and with the direct contact, but it is of course a consideration, because now I'm going to talk about the key considerations for these different technologies. And with a direct contact condensing economizer, which is the one you've just asked about. So when we're spraying on the burner, and I'll get to your question first, in a natural gas boiler, let's start with natural gas, because of course your question can't be answered broadly, because if you're burning dirty fuel, it's a different answer. With natural gas in a direct fired water heater, when the water passes once through, so I'm simply taking 100% fresh makeup, I'm heating it to 180 F to 90 Celsius once through, it's still potable water. And that's been determined through, multiple tests. Natural gas is clean. We cook with natural gas at home. So in a one-pass system, the pH shifts by about 0.5. So it does get a little bit more acidic, but it still qualifies as potable and has been used in the food and beverage industry directly in process and sanitation with a direct fired unit, no issue. If you recirculate the water, I guess I'm getting a glare there now. I might do something about that a little bit later. Is that coming in through the back? Sorry about that. But if you recirculate the water, so now I'm recirculating, it's not once through. The worst case is you reach a pH of about 4.5 because of the absorption of carbonic acid or absorption of CO2, which creates carbonic acid. So that circuit would be stainless steel or even PVC or CPVC. PVC is kind of low on the temperature end. But so the short answer is, in a recirculating system, you will become slightly acidic, carbonic acid. So we typically have those circuits in stainless steel. So on a once through, it's potable. On a recirculating system, you may need some pH adjustment, but at the same time, if you're using stainless steel, the pH of 4.5 and carbonic acid is not an issue. So is that okay for the question, Mark?
Yes, absolutely. Thanks.
Okay, and so I'll go on about this option. The other thing is, it's the most efficient economizer when you have more users than heat source. We're going to talk about this more. Source, there's the glare's kind of go. Source and sink limited. When you're developing projects in heat recovery, you either have more waste heat available than you have user, or you have more user available than waste heat. If you've got more source than sink, we call it source limited or sink limited, because the user is going to dictate your project size. If I can recover 10 MMBTU, but I can only use 5, I'm going to build for 5. But if I can use 20, but I can only recover 10, I'm going to build for 10. So we call that a source and sink limited situation. When you have more user than source, then this is the best technology because it can squeeze the most heat out of the source. It's also got the longest life. That's because the acid drops that develop when you're condensing, the small acid drop is immediately neutralized in a huge shower of water. So you don't get spot corrosion, spot condensation. However, with this type of system, you typically need a fan and a pump, whereas sometimes indirect contact systems can go in without a fan and a pump. And with a direct contact system, you get a lower temperature. You produce water at the wet bulb temperature. It's basically a cooling tower being used for heating. And so in a typical boiler exhaust, you can make water at 50 or 60 Celsius, 140 to 150 F. It can produce higher temperatures in a hot, humid exhaust, but I'm kind of focusing on the boiler exhaust. And in a natural gas boiler exhaust, a direct contact system will only get you about 140, 150 F, whereas an indirect system can get you higher. And of course, a direct contact system is a wet scrubber, so it can handle a wide variety of dirty exhausts as well. So those are a couple of the considerations for a direct contact condensing economizer. For an indirect contact condensing economizer, now my water is in a fin tube and the condensation occurs on the outside of the tube. I can get a higher temperature much more easily. So if I've only got a small heat sink, I've got this much waste heat available, but I've only got this much user. Now my savings are not dependent on how much heat I can recover. It's dependent on how hot I can make the user. Classic example, boiler makeup water. If I've got a huge amount of waste heat and only a small boiler makeup water load, then my savings will be dictated by how hot I make that boiler makeup water. My savings will not be dictated by my source. My source, I've got more source than I can possibly use. My savings will be dictated by the temperature I can bring my sink to. But in the case of having more sink than source, my savings are dictated by how cold I can make the source. So source and sink limited, different design considerations, and hopefully it becomes clear as we move through this as well. So it is less complex than a direct alternative because it often can be installed just like a feed water economizer. So, you know, your water's already got pressure. It doesn't lose the pressure going through the economizer. In a direct contact system, because you shower over the water, you end up with a sump full of water, which then needs a pump. And a direct contact system has a higher pressure drop. So an indirect system can be less complex. No fan, no pump in many cases. However, the life is absolutely shorter, without question, because when you get a droplet on the outside of a tube, even if the tube is stainless steel, that droplet is an acidic droplet. You get a dielectric effect, you get an acidic effect. And so with indirect units, within 5 to 10 years, you're certainly going to be doing tube repairs and replacements. And in addition, it's got limited dirty exhaust application. Direct contact, for example, works beautifully on diesel without problem. Indirect contact, diesel has too much sulfur, and you're gonna ruin those tubes, not in 5 to 10 years, but in 5 to 10 months. And now, we just extend it really, because now we just put a burner in them. So now with a direct contact condensing boiler, so now this is the shower over the burner, it is absolutely without doubt the most cost-effective option to heat water without exception, honestly. If you've just got a water stream that you've got to heat to 80 degrees Celsius and you're going to use a fossil fuel, natural gas, this is absolutely the most cost-effective way to do it. There's no pressure vessel involved. That's why, because it's a shower and a flame. So you've got a burner, as does a boiler, but you've got no pressure vessel. And so it becomes a very cost-effective and simple installation. It's got the longest life. The only thing to fail truly is a burner. And the systems do last 30 years. To the question that was asked, Mark, it's clean water. It's potable when it's once through, but there's some treatment for recirculation. And they're typically limited to about 200 F. So, however, it's not the most common hydronic boiler hot water heater that you're going to want to go over 200 F. But we must return below the dew point. We must run in condensing mode. And this is where I'll get a little bit technical. I want to check in on my timing, Mark. How long should I be chatting for?
You have at least another 15 minutes.
That's what I thought. That's
Sure.
and that's still leaving room for questions. Okay, no, I think it's going, then I think the timing is good. So yeah, so in this, you're limited to about 200F, but one of the things I'm really going to focus on here, because I've got a very interesting story about someone running a direct contact condensing boiler in evaporative mode, which some people don't even think about. And certainly these operators never even considered it. And when I was finished, they still didn't understand what I was trying to express. I hope I get to express it better to you folks. And then there's an indirect contact condensing boiler. So now we got the flame on the and the combustion gas on the outside of the tubes, but we got cold water going in the tubes. And so we're condensing on the outside of those tubes. I've been looking at this for some time, and I'm going to make the bold statement they should never be used. And I'm going to say that because a traditional hydronic boiler, which lasts like 30 years, if it's not a condensing hydronic boiler, it lasts for a long time, and an external condensing section will be superior in almost every case. Buying a condensing boiler versus a traditional boiler with a condensing stage separate, there's no comparison. The traditional boiler and condensing economizer combo has a longer life because the hydronic boiler will last forever, and the condensing stainless steel section is external to the boiler. It's got even better performance. You wouldn't think so, but I'll weave the tale of why we get better performance by having the boiler and the economizer separate. I'm hoping some of you are surprised by me saying, well, a condensing hydronic boiler won't deliver the same. Yep.
Oh, I didn't see that you unmuted, but I was just going to ask, does this mean, what about for like oil boilers? Because I think in my understanding is that condensing ones are not the greatest idea, but if you do it separately, like you're suggesting, does that mean now there is an application to add this condensing section to a traditional, mid-efficiency oil boiler?
Absolutely. Absolutely. But in that case, I would not recommend an indirect, because the indirect will still suffer from sulfuric acid dew point, and will corrode. But you can take a traditional oil boiler and put a direct contact unit and achieve condensing efficiencies.
Okay, and somebody's asking how much water is consumed during operation of these boilers. I'm not sure.
No water is consumed. Water is produced. We are condensing water from the flue gas. We are making water from the flue gas. And the beauty of that is it creates a blowdown, a continuous blowdown without ever adding water. Because we're cooling the flue gas to below its dew point, we're creating water, which at our food and beverage facilities, we return to their cooling tower systems and reuse the water and claim, although it's not worth a lot of money, we're able to claim huge water savings as well. Whenever you put in a condensing system, you're adding water to your facility, not using it.
Right. So the water that would traditionally evaporate, you're actually reclaiming that as well, right?
Well, yeah, the water that would leave in the flue gas. When you burn the CH4, you've got H2O in the flue gas. We're taking that out by cooling that flue gas to below its dew point.
Yeah, so in a traditional system, water would be consumed in a sense, because like you have your makeup water, because some of it evaporates, some of it could be steam, condensate that's not returning back to the plant. There's various reasons.
That's right. In a boiler system, you have makeup for various reasons, but you also have blowdown to keep it clean. So you blow some out in a boiler circuit, in a steam circuit, and then make it up. In this kind of system, you never need to make up water. If it's operated and integrated properly, you can actually recover water from it.
Okay, hopefully that answers the question. And then I guess another one, since I have you, according to your experience, what's the recommended heat exchanger material when you are recovering heat from flue gases from bunker fueled boiler, diesel fueled boilers? I think that kind of, when I brought up the oil boiler, I'm guessing it's similar to that, right?
Yeah, bunker and diesel. Now, Diesel is one step, bunker's another. Diesel, no problem with direct contact using stainless steel. Bunker, and it depends on sulfur. I have to qualify, there's low sulfur diesel and yeah, but I'm basically using traditional levels. In bunker, the sulfur levels are so high that your 304 and 316 is no good. When we're doing diesel, I think we usually do 316. I'm not a metallurgist, but it's been a while since I've actually been right in the design state. But it's always stainless steel. On natural gas, 304, 316. On diesel, similar, or it would probably be 316. On bunker, becomes a different thing. You can look then at coated tube solutions. There's Teflon coated tube solutions. There's plastic heat exchangers out there that are good for high temperature, but direct contact becomes a wet scrubber and you end up with a huge water treatment concern. So, just to do heat recovery, the direct contact wet scrubber is not ideal. And you have to go to exotic metals, Hastelloy, or even fiberglass. And the indirect unit certainly can't be used on on bunker. I'm sorry. On bunker, you would have to go with the more severe, and I would probably recommend, the Teflon coated or even plastic heat exchangers that are available, designed specifically for high sulfur streams. Okay. And so indirect contact condensing boilers, again, now we're with the, as I said, water in the tube and the flame on the outside. That two-stage thing, as I said, you can actually get better performance by separating the hydronic boiler and the economizer and lower cost. And I'm going to describe why. So it's more cost effective, it lasts longer, and it gives you the opportunity to be more efficient. In my opinion, we should never be installing or condensing boilers anymore. If anybody wants to achieve condensing efficiency on their hot water circuit, you're much better with a traditional hydronic boiler and an economizer, or you're better with the direct fired water heater. But an indirect condensing boiler, I honestly can't see a situation where I would recommend one. And here's just an image of what this is a traditional hydronic boiler with the economizer external. So you can see it's quite simple. And so this boiler will last 30 years, and this economizer will need some tube replacement, which is quite simple and can be done external to the boiler, and of course much lower cost. So and it ends up being a similar size. And the reason for the performance difference is if you hook this up to a hospital, for example. Actually, I think the graphs coming up display that better. So, but here's a recent example. This is, an example where I'll just read it. The project was over budget. This was a project where people were looking for a condensing boiler. And the condensing boiler project was significantly over budget. They were looking for a condensing indirect boiler, and they were seeking value engineered options. The condensing boilers per spec came in at 1.2 million, and the traditional boiler economizer approach was at about 800,000 with longer life and likely better performance. So yeah, that's an example, and this is why I'm so hard on this one point. Now here's a neat curve. This is the story of about a gentleman working for, I won't say the company, but Fortune 500 food and beverage company, running a direct contact water heater. So this is now flame with a shower. And this gentleman was saying that his exhaust temperature was about 160 F. So he was very pleased with his boiler efficiency. I don't think any of you right now are saying 160 F, that's terrible efficiency. What? No, you're probably all saying, yeah, I'd say the same thing. Going out at 160 F, that's beautifully efficient. I want to spend a little bit of time on this heat recovery curve. So this orange part, this indirect contact water heater curve, that's the same curve we've looked at a few different times. That shows that as you cool the exhaust gas, it shows what your efficiency is. So this is an efficiency curve showing if my exhaust gas from a indirect contact heater is 210, then my efficiency is about 85%. The green curve is the efficiency curve for a direct contact water heater. So a direct contact water heater, I'm going to pick that 160 degree point that my customer had. And so my customer was imagining they were sitting about here, that look at this, I'm at 85, 86% efficiency because I'm going out at 160. Well, you cannot use these curves for a direct contact water heater, because in a direct contact water heater, your exhaust is 100% humid. And when your exhaust is 100% humid at 160 degrees, your efficiency is actually 72%. And it plummets because a direct contact heater is spraying water into the flue gas. So if you imagine, it'd be like going to a traditional boiler and spraying water in the stack and cooling the water down by spraying it in the stack and then saying, now it's 160 degrees Fahrenheit, and so my boiler is more efficient. No, it's just that your waste heat is now latent heat instead of sensible. So be very cautious with direct fired water heaters, because if you are exhausting above the dew point, one, you're evaporating water, and you should never run in evaporative mode. Your control system should make sure you avoid that. And two, your efficiency is dropping exponentially. And should you happen to go out at 170 F, you're just between 55 and 60% efficient. So a direct contact water heater can be tremendously cost effective and efficient, and it can also fool people into thinking that they're running efficiently when they're not. So I know that's a deep subject. It might not be fully grabbed, but happy to have discussions, answer questions. And here I'm going to give a little example about the integration as well. Here's a heat recovery curve. Here's 15% excess air, 50 degrees Fahrenheit, exhaust temperature versus efficiency. So that's the normal curve. And let's talk about a traditional heating system. Let's go into a hospital, a whole bunch of heating circuits, you know, basically the bulk of it's at 180 to 160 F. There's some small colder sinks, you know, but if you put all the users together, the return water temperature, that shouldn't say 220 F, but the return water temperature is going to be 140 to maybe 180 F. So that's the temperature of all, you know, the circuits are going out. There's no steam out there. It's all liquid circuits, hydronic circuits. They're all coming back to the boiler plant. You put them all together and they're coming back at 140 to 160. So let's just say we're coming back. If the circuit is coming back, I'm going to go in the middle here, 175. So that circuit from the plant's coming back to the boiler, to the water heater at 175. If it's coming back at 175, I can only cool the exhaust to maybe 190. If I can only cool the exhaust to 190, this is where my efficiency is. So that's great. That's wonderful. I've put in a condensing boiler. I'm not cooling it down to the dew point, so I'm not putting in a direct contact system. It's not cold enough for me to put in a direct contact system. I put in an indirect condensing boiler or a traditional boiler and an economizer, and I bring all of that hot water back and I run 86 to 88% efficiency. Here is what can be done differently. If you selectively separate those users, because as I said, we've got this massive user at 180, 160, and then some smaller cold users. So if you separate those users and you hook up the 180 loop to the hydronic boiler. So the hydronic boiler is serving 160 in, 180 out. The hydronic boiler is working at 82% efficient, not condensing. Then you take the exhaust gas from the hydronic boiler and you use that to heat in a condensing economizer. You use that to heat the colder sinks. So you keep the hotter water and the colder water sinks separately. That way you don't have to, and what happens if you do that, if you selectively put the low temperature sinks to the economizer and the higher temperature sinks to the boiler, what that means is I'm using that cold small sink to cool that exhaust at the final stages. And it can be a tremendously different result. So
Robert, what about in a building where you need that 180 in, you know, under peak design conditions, but then you have a reset and you're going all the way down to 120 depending on your outdoor air temperature? Would you have a combination of non-condensing and condensing so that you can use the condensing boiler when it's milder temperatures outside, and then still attach your separate, you know, condensing unit to the non-condensing boiler? Or how would you do that?
Yeah, now, you're getting into, like modeling, and we'd have to look at, how things are balancing out. But the bottom line is, if you're able to come back to the system, if you're able to use water, I shouldn't say use water. If you have water users down at 120 or 110, then yeah, having a condensing stage is going to dramatically increase your efficiency. And that can be done either, again, in an indirect or a direct fashion. But that's a controls question, where we would run that water. But yeah, you wouldn't want to run the 120 through the hydronic, the traditional hydronic, because then you'd blow it out. You'd be condensing in a traditional hydronic boiler. That would be bad news. So then you'd have to have some controls and make sure that anything cold is going through the stainless steel condensing economizer, and anything, because in a case like that, you can also preheat in the condensing. If everything's cold, you could put it all through the condensing economizer and then all through the hydronic boiler. So it can be done, Mark, but that comes down to a controls question. All right, but the big picture is, by separating cold and hot users, even in a hydronic circuit, your efficiency with the exact same system, and it hasn't gone up 1 or 2%. Those 40 degrees are in that critical curve. Those 40 degrees difference, because we're heating the cold sink separate from the hot sink, it doesn't give us 1 or 2% difference. It gives us 5 to 10% difference just by hooking up the sinks differently, separately with the boiler. So that's an integration consideration that I've almost never seen in the field. And of course, heat recovery is, what I've been doing my whole life, and optimizing large systems. And this is something that is commonly done, but I don't see it out in the field. So considerations, instead of looking at a hydronic system and a plant and a facility as one big heat sink, think about the different heat sinks and how you can stage and apply your heating with pinch principle to get the highest efficiency, rather than just blending all the 180 and 160 and 140 sinks together and trying to hit them with one big hydronic loop. You're missing a huge opportunity. So other considerations: installing condensing, selectively convert, yes, makeup air heating. That's one of the good ones, by the way. Hospitals typically have a bunch of 100% fresh makeup air. You could do that with a really cold circuit. You could put a separate glycol circuit. You could go out at 120, and in the wintertime, you can come back at 60 Fahrenheit. You could do all the air heating, but you don't have to convert the whole plant. Just convert a couple big air makeup units to take advantage of the low temperature of that heat sink, and then hook up that low temperature heat sink to the economizer, not to the entire circuit. Boiler makeup heating, domestic hot water heating can all be done with heat recovery. So yeah, what's the result? A very low final exhaust temperature of 80 to 120. Got to make the one comment about 100% efficiency. A system installed in Memphis, Tennessee, 100-degree Fahrenheit outside air temperature, boiler exhaust temperature 90 degrees Fahrenheit. So the boiler exhaust was colder than the combustion air. So actually the system was gathering heat from outside air, and that's why it was more than 100% efficient. It was using all the energy we added with fuel and was taking some energy from the hot, humid Memphis air. So the systems can be designed to be quite efficient. And that would be the goal. By separating the sinks, you can achieve much higher efficiencies and get down that curve. Those 20 to 40 degrees are a bigger deal than the whole feed water economizer thing, which people have been playing with for decades. So again, I've been focusing strictly on this. So now I want to talk about kind of the lie. Some people would think, well, I'm going to go from steam to hot water, and I'm going to do hot water condensing. My efficiency can go up. I can tell you, I can get that thermal efficiency without converting from steam. You could keep your steam on a steam boiler. You could take your cold users and hook them up to the economizer, and now your thermal efficiency will be the same as a condensing boiler. You can get condensing boiler efficiencies with steam boilers by putting condensers on them, condensing economizers. However, then you're not dealing with all of this stuff. Then you're not dealing with because you still got steam going through the plant, you've still got leaks, you've still got a higher temperature heating system, which means more radiation losses. You've still got steam traps, which are difficult and a nightmare, blow down. So if you want to just try and get your steam plant efficiency, thermal efficiency way up there, you can have condensing efficiencies by just adding an economizer. The same boiler efficiency as any condensing boiler you can have with a steam boiler and a condensing economizer. But of course, that doesn't eliminate the rest of the issues with steam moving through a facility. So just another consideration when you're looking for your savings in your project. So summary. Heat sink temperature is key. Condensing boilers don't have efficiencies. Their efficiencies are completely linked to the return temperature of the water and the exhaust temperature of the boiler. Not like a steam boiler. Steam boilers always have the same return temperatures, but it's hypercritical that when you're considering condensing technology, that you look at and optimize your heat sink temperature, sometimes even by retrofitting infrastructure to operate at lower temperatures. Best option is absolutely dependent on the nature of the heating load and the relative proportion. Do I have more user than source? Do I have more source than user? 9 out of 10 times you got more source than user. Very rarely are you able to use more waste heat than you have. Very high system efficiencies can be achieved. Condensing systems without consideration to appropriate load temperatures provide only a fraction of the benefit that they can. Direct contact water heaters and traditional hydronic boiler economizer combinations are a more economical and reliable option than condensing boilers. And integration is as important or more important than the boiler or heater technology or rated efficiency. And that's it.
There don't seem to be any more questions. I think that means, Rob, that you did a great job. You really did a great job explaining the ins and the outs of heat recovery.
I hope so.
Although the one thing that occurred to me while you were chatting was, the importance of application engineering. In all the years I spent in an engineering house, I think my observation is perhaps too frequently we as a set of disciplines are catalog shoppers for technology. And in this particular case, I feel like catalog shopping is not the way to go. Is that an accurate assessment?
It's yeah, I would say so. And to be fair, the reason we've been able to look at things like this is because we've worked mostly in industry. So we're looking at a $10 million fuel bill at a big food and beverage plant. And so this kind of optimization, they can spend a lot of money on engineering and optimization because it's a big project, big impact. When you start getting into, smaller hospitals and the bid spec world, things are so driven by price. And yeah, the catalog shopping becomes the way, but we absolutely don't, Andrew, to that point, when we build a system, our coils are not designed to use water or glycol at 180. Our systems are designed to go out at 130 to 140 and to come back 20 or 30 degrees hotter than the outside air. And then that is not catalog shopping. When we phone our coil suppliers and tell them what we're doing, they say, what the hell are you doing? Why don't you go out hotter? You're going to have a smaller coil. I said, yeah, our job is not to get a smaller coil. Our job is to be energy efficient. But again, once you get to small institutions and commercial, the custom engineering element becomes a relatively large fixed cost, which smaller projects often can't support. So I don't want to trash catalog engineering, because if people don't want to pay for engineering, well, then catalog engineering is the way to go. Yeah.
Well, but you get what you pay for. So
absolutely. And in our cases, these systems, and I'm talking large system, hundreds of thousands, even 1 million CFM affected, that we convert steam coils to low temperature glycol and have massively efficient boiler plants in big industrial facilities.
You're right on. So there's a couple more questions popping up. So hopefully you're able to answer some of them. One of them is, just as a really kind of top-down look at capital cost differences between a traditional condensing boiler, those catalog buys that we make that we all think we're doing a great thing for the environment, versus a more conventional boiler with a bolt-on condensing heat recovery package, like in the 5 million BTUs or less. category?
Yeah, I'll just stick with the number that you guys saw, which was 800,000 versus 1.2 million, which is, 33% less or 50% more, however you'd like to slice it. And we've seen that repeatedly. So there's a company, Boiler Room Equipment. We purchased this company a while ago, and so they have actually partnered with with Hearst. And, Hearst has, a skid mounted economizer and hydronic boiler because they also believe in this approach. And so honestly, I would say you're looking at a 35% difference comfortably.
Yeah, right on. And that's first costs, right? That's capital.
Yes. Yeah, that's just the capital on the unit. Yeah.
What about on a life cycle basis? Have you guys ever run the numbers on that? I know for the clients that I work with, life cycle costing is a big driver. There, of course, yes, you have to budget for that first cost, the capital outlay, but the reality is, when we make decisions on technology into our buildings, we live with those decisions for several decades in a lot of cases. So have you looked at the cost comparison on that basis?
It's a good question, Andrew, and because we come from somewhat different backgrounds, like the 20 and 30-year scale, we often are looking at the 5 and 10-year scale. So the short answer is no, but it would come out. I don't know what kind of lifetimes you guys carry for condensing boilers. I'd be surprised if it's past 15 years. Whereas with a hydronic boiler, you could carry 30 and then look at the economics about changing out the tubes in the economizer. It would be a bigger winner in the longer term scenario. You're right, Andrew.
Yeah, I mean, I think more and more, as we tackle, climate change, the impacts of using fuel to do the work that we all appreciate at the end of the day. I think life cycle costing is becoming a bigger driver for many organizations. So, I mean, that's not really what you guys have to do necessarily, but certainly one that many of us energy engineers are really faced with.
Yeah, and of course, there's the additional driver now, as everyone knows, don't need the separate, but the carbon tax is going to enable engineers to do more detailed and clever and innovative work to try and achieve the reductions because the customers are going to be paying more money for their natural gas due to carbon tax. So I think the opportunity for us to do more clever work is coming in the market.
Yeah, you bet. Another question here. What's the maintenance frequency for the heat recovery economizers that you've been talking about through this presentation?
On natural gas, nothing. Natural gas is nice and clean, really virtually nothing. And we do have systems running for 30 years, like a 30-year lifetime's not speculative. I've seen direct contact systems from multiple suppliers installed and working for over 30 years with very little cleaning. If you're running a dirty fuel, you're going to be looking at cycles 6 to 12 months. The interesting thing, that's application specific. As soon as you get into dirty fuels, everything's different. Different particles are different. But of course, the direct contact unit's a wet scrubber, which is used for pollution control. So they're pretty robust. But when you go with the fin tube systems and you start getting into corrosive or particulate, then the fin tube is not ideal and the direct contact takes over. And you even start stepping away from direct contact complexity and reducing the complexity of the packing inside that scrubber to make it more amenable to a dirty stream.
Okay. Here's another question. So throughout the presentation, you've thrown lots of great efficiency numbers at us, and I didn't write any of them down. I'm trying to catalog them in my mind, but I wouldn't be able to pull them out without a deck of slides. But somebody's asking for the numbers that you've quoted for the overall efficiency when you add an economizer to a traditional or conventional hydronic boiler. How do those efficiencies hold up when you have a highly variable load within the facility? Like a school, for instance.
Yeah, that's a good question. Those efficiencies exist for a moment in time. That's a very good question. It's not like a steam boiler. Those efficiencies, well, it is. It's just the variation is much higher. Boilers efficiency also varies, but they have a much more consistent return. And so that's where the controls actually come in. It's a good question. for example, in a direct contact economizer, I was talking about the spray economizer. If you don't have any more load and you keep circulating that water, you'll begin to evaporate, right? That water is still going into the flue gas, but I have no more user. So now that water is coming back hot. Now I'm not cooling the flue gas, I'm evaporating. So you have to build in controls that say I'm returning at a hot temperature. There's no more heat sink. And now I just put the flue gas back up the stack. And I don't recover heat from it. But it requires integrated controls for the variable load. And again, the problem, Andrew, you mentioned you want a catalog shop for this. Well, how do you tell someone how much they're going to save? You cannot tell them how much they're going to save based on the efficiency of the unit.
Yeah.
That is, so it's a very good question. The way that we would tell them how much they save is either an hourly or daily model of return temperatures to the unit. And with those daily or hourly return temperatures to the unit, you know exactly the performance you get at that point in time, and that's how you model savings. But you can't possibly say your steam boiler's 80%, and under this average condition, we expect 90%, and here's your savings. You want to build the case, you have to model.
Yeah, I think that's therein lies the rub, right? Application engineering, asking good questions, making sure you disclose all of the characteristics of all your design requirements and the operational characteristics of your facility. These are all, perhaps it goes without saying, but critical, right, to engineering a good system.
Yeah, And these models, again, it's a standard part of the applications that we do.
Yeah, right on. So the last kind of technical question, and it's kind of an open-ended one, but Rob, do you have any recommendations for places where folks can go to read more on these things? So somebody's asking recommended resources. Clearly, you've struck a nerve with some people, and they're looking to feed.
Well, I'm a bit of a resource, Andrew. So obviously I'm here. I work for Thermal Energy. That's what we do. I have some papers that I could share as well. I have some other publications on condensing technologies. But do I have a Bible that I go to? I don't.
Okay. So to that point, being a resource, I noticed you have Antoine's email up on the screen. Are you able to share yours as well with the audience?
Yeah, absolutely. It's just Robert Treby at thermalenergy.com. So you see the name up there, and so it's the same as Antoine's, but
same form factor, different name.
You got it. Robert.Treby at thermalenergy.com. And I'd be happy to have, discussions with people who have some technical questions. Yeah,
that's awesome. Well, listen, Robert, we really appreciate you taking the time this morning to educate us. It was a great presentation, and judging by the questions and answers during and after it, you've got a lot of people thinking. And I think perhaps the most interesting conclusion that I've drawn, out of this, and perhaps, the naivete of not knowing enough sometimes, is that. Condensing boilers, I would have often thought, hey, condensing boiler is the way to go. You get it all in one package, and you got this great efficiency. But what you're enlightening me to is that perhaps another look at cascading sinks and perhaps a more engineered solution is perhaps the better way. So
I was really hoping that I would say some things that would make a few people say, well, wait a second. I just hope because I touched on a lot of things. I didn't detail much, but if I touched something that made you, think a little, that's what I was hoping to do. So I'm sorry if it was a bit scattered, but it was also intended to say a few points and bullets that ideally get people standing up and furling their eyebrows. But I hope that what I've presented is accurate, and I'm confident that it is.
Fantastic. Well, again, thank you very much. We appreciate you coming out. I'm just going to share my screen just for a second here because there we go. Because we'd like to just give a shout out to the next the next webinar. It's actually only a few weeks away, and we've thrown this one in here because we noticed that there's some new features in the AEECE package for thermal energy network design and analysis, and we thought that the chapter might have some folks that would be interested in that. Certainly, if you are involved with thermal networks, either from the operation or the design perspective, this might be a good one for you. So if this webinar is of interest and you haven't signed up, please do. You can find it through our website, through the event calendar. We've put it on our LinkedIn as well. So please consider doing us a favor and signing up for the next webinar, which is only a few weeks away. So thanks very much, everybody, for coming out to today's webinar. We really appreciate it, and look forward to additional webinars throughout the year. We have a full roster of webinars planned, and hopefully they're as informative as this one. Thanks a lot, everyone, and have a wonderful day.